Ramanujan for G is now available on the Google Play Store. Try it out for free.
Good morning, students. Today we are going to start a new topic, colloids. And in previous chapters, as you remember, as you know, we have studied about solutions, and also we have studied about the heterogeneous and homogeneous mixtures. And we know a solution is a homogeneous mixture, and a heterogeneous mixture is defined as if the component of the mixture are not uniformly distributed, and homogeneous mixture components are uniformly distributed. One example of the heterogeneous mixture is the suspension, and the suspension, the examples of suspensions are mud and water, mixtures of mud and water, flour and water, or suspension of solid pigments in water, which is known as tempera paint. And these suspensions are heterogeneous mixtures composed of relatively large particles visible through naked eyes or a magnifying glass. Suspensions are cloudy and the suspended particles settle out upon a standing. These points we know about the suspension. So they are cloudy and the suspended particles they settle out upon a standing or when they left undisturbed. So now on the other hand, we know about the solution. A solution is a homogeneous mixture in which dissolved species are molecules or ions, and in this no settling occurs. So dissolved species are what the ions and molecules, and these ions and molecules we call as usually solutes because they are dissolved and they are dissolved in a solvent, and the solvent, the component of the solution is larger in amount is called as a solvent, and the one which is smaller in amount is called as a solute. And so what we say solute is dissolved in a solvent. And so the solute particles, if these particles are actually ions or molecules, they can be ions or molecules, they are distributed uniformly throughout the solution and means they are distributed in the and so the continuous phase here is the solvent phase. And in this continuous phase, some solute particles here and there, they are distributed uniformly. The solution exhibits completely different behavior from suspensions, and this is what we have seen. The solution may be colored, but it is transparent. So what we see, suspensions are cloudy and they are opaque usually. But the solutions are what? They are transparent, although they may be colored, like zinc sulfate solution, sorry, copper sulfate solution. If you look at copper sulfate solution, it will be blue in color, but it is transparent. The molecules or ions are not visible. And so in solution, the ions or molecules are not visible. Whether these molecules are the solute or solvent or the ions of the solute, they are not visible because they are so small that we cannot see them and they do not settle out on a standing. And the solute particles do not settle out on a standing or when they left undisturbed. So as we now till now we know about the suspension heterogeneous mixture, this particle gets settled out. These particle size in suspension are very large, relatively large particles, and these particles are visible through naked eyes or the magnifying glass. Now the third kind of mixture is what we call the colloid. And the mixture, the another class of mixture is called the colloid, and these colloids are also called colloidal dispersion. And these colloids or colloidal dispersions exhibit properties intermediate between those of suspension and solutions. So their properties are usually intermediate between solutions and suspension, and some of their properties sometimes will resemble to the suspension, or some of their properties resembles to that of the solution. Usually, it is between them. And for example, the particle size, if you look at the particle size, the suspension particle size is very large. However, in the solutions, we know the particles are ions or molecules, which are, we know they're very small. They are less than 1 nanometer in the dimension. But if these molecules or ions, if they aggregate in certain numbers, maybe 100 or 1,000, so they form a particles of the colloidal dimension. These particles in the nano scale, nanometer dimension, and these are nanoparticles, and these nanoparticles usually forms colloids. So this is another class of mixture called colloids or colloidal dispersion, exhibits properties intermediate between those of suspension and solutions. The particles in a colloid are larger than most simple molecules. This is what I have just explained. However, they are small enough to not settle out upon a standing. So, although they are large particles, they are aggregates of molecules or ions. However, they are not large enough to get settled out upon standing, as we see in the case of suspension. Suspension also the large pieces are they are large pieces of particles, the crystal or something, but they are much larger, and so they will easily get settled out. The example you can see in this figure here. So this is an example of the solution. You see the homogeneous mixture particles of solute are uniformly distributed and the particles are very small in size, and the blue color that you see is the solution. It is shows the color of the solvent. And the example that you can see here that the mix is the salt water in the aquarium. So the salt water in the aquarium that is shown here is the example of the solution. Now we see another particle that is colloid, that is class of another class of mixture, and this mixture, so this is a colloid, and you can see the colloidal particles are much larger than that of the solute particles into the solution. These particles are much larger, but are not uh, so large that they will easily get settled out. And also what we see, their distribution is not homogeneous, their distribution is heterogeneous. As you see in the case of solute, the solute particles are homogeneously distributed. Means all the components are homogeneously distributed. This is a binary component we have from the solute and the solvent. But and it is how one can, because the distance between you can see the solute particles is same in all the cases. Now in the suspension as shown here, the representative case, these particles are not uniformly distributed, so this is a heterogeneous solution, heterogeneous mixture, not solution, a kind of heterogeneous mixture and heterogeneous mixture. But what we see, the particles do not get settled out, and we cannot easily visualize them through the naked eye or even through the magnifying glass. And the example is the milk, that we know in the milk was a butter uh, fat is butter fat is dissolved in water. So butter fat, when it makes a solution with water, it's not a mixture, heterogeneous mixture with water. The example is the milk, which is also called the emulsion. What is an emulsion? We will see later on. Now the another the suspension, and the suspension here is such as uh, uh, such as mud is a heterogeneous mixture of suspended particles that appears cloudy and in which the particles can settle. And you can see in this figure that these particles are much larger even than the particles in the colloids. So these particles are of the colloidal range, and colloidal range is the particle size should be between 1 nanometer to 1000 nanometer. And these particles, if the particles in suspensions are their dimensions are more than 1000 nanometer, and in solution, true solutions, the particle size is less than 1 nanometer. And so the particles in a colloid are large enough to scatter light. So they scatter the light particles in colloid, scatter light, and this phenomena is called the Tyndall effect. And this Tyndall effect we will see later on when we will study the properties of the colloids. So this can make colloidal mixture appear cloudy. So these particles are large enough so they make this colloidal mixture appear cloudy or opaque. Or this opaque means they are more translucent, such as the searchlight beam shown. And the searchlight beam, as you see, is shown here. And this is because you can see the path of searchlight, because searchlight passes through the colloidal charged particles, and you see the and the clouds are colloidal mixture composed of water droplets that are much larger than the molecules, and these water droplets are much larger than the molecules because it's the aggregate of many molecules of water, but they are not so large that it will easily get settled out. So these droplets much larger than molecules but small enough not to settle out. And the path of such light beams are made visible when light is scattered by colloidal sized particles in the air, and these colloidal sized particles are the particles of fog and smoke. And that is why this path of such light is visible. And if the path is not visible, based on that you can see what is the moisture content and other things into the atmosphere. Now let's look into the term etymology of colloid. The colloid word, it is made up of the Greek word. It's made of Greek words because of the combination of two Greek words, pola and eidos. Pola means blue. It means pola has the meaning blue, and eidos meaning the light. So it means colloid means blue light, and it was first used in 1861 by Thomas Graham to classify mixtures such as starch in water and gelatin. So colloidal particles have enormous surface area per unit mass due to their small size, and how one can realize how uh, large the surface area of the colloidal particles are, the particles in the nano, that we also call them the nanoparticle range, the nanoparticles. So if you look at the example, consider for example a cube with 1 centimeter side. So a cube with having 1 centimeter side will have a surface area, total surface area, it will have faces, and so each face will have the surface uh, area equal to square centimeter. Six faces will have total surface area of 6 centimeter, square centimeter. And now the volume of this cube will be equal to 1 into 1 centimeter into 1 centimeter, 1 centimeter, so 1 cubic centimeter. Now, suppose if this 1 cubic centimeter size cube is divided equally into 10 to the power 12 cubes, and if it is divided into 10 to the power 12 cubes, the volume of 10 to the power 12 cubes should be equal to the volume of one larger cube, and so 10 to the power 12 cube 10 to the power 12 into the volume of the smaller cube should be equal to the total volume of the larger cube. So 10 to the power 12 into, suppose the now the side of the smaller cube is A. So 10 to the power 12 into A cube should be equal to 1 cubic centimeter. And so what we get, the value of A is equal to 10 to the power minus 4 centimeter. So the each side of the smaller cube will be 1 centimeter in length. Now one can get the surface area of each smaller cube, and the surface area of each smaller cube will be what? Length into width, because A is square, and A square will be 10 to the power minus 4 centimeter into 10 to the power minus 4 centimeter. So it will be equal to 10 to the power minus 8 square centimeter, the area of one face. And since each the smaller cube will have six faces, the total area will be equal to 6 into 10 to the power minus 8 square centimeter. Now what we know, the larger cube is divided into 10 to the power 12 smaller cubes. So total surface area of 10 to the power 12 smaller cubes will be equal to 10 to the power 12 into 6 into 10 to the power minus 8 square centimeter, and this will be equal to 6 into 10 to the power 4 square centimeter, means 60,000 square centimeter. As the 60,000 square centimeter means 6 meter square. So what we see, one larger cube, when this was at one larger cube, its total surface area was only 6 square centimeter. But when we divided it into 10 to the power 12 cubes, and with these cubes would have the dimension of the large colloidal particles, and that is why 10 to the power 12 is taken into the consideration, and each cube is having the size of the large colloidal particles, and when the colloidal particles total surface area, when we have added it, has become equal to 6 meter square, and so you can see the surface area has increased enormously. And if these colloidal particles they behave as a catalyst, you can see the surface, as we have seen earlier, that the surface area of a heterogeneous catalyst is increased. And so all the catalysis, not only the reaction rate increases if the surface area increases because of the adsorption. And so the catalyst surface area increases because of the adsorption. The catalysis increase, the rate of reaction will increase. And that is why in the nanoscale uh, but we see the catalysis which is more efficient, and this catalysis is usually the heterogeneous catalysis. So this enormous surface area leads to some special properties of colloids, and those things are not there much in our syllabus. Let us now see the difference between true solution, suspension, and colloidal solution. So what we have seen till now, the true solutions, they are homogeneous mixture, but the suspension are heterogeneous mixture, and colloidal solutions also we have seen there heterogeneous. So this is also a heterogeneous solution, which is a suspension, and this is also a heterogeneous solution because these particles, the components of the mixture are not uniformly distributed, so they are heterogeneous. But the solution is a homogeneous mixture because components of the mixture, this homogeneous mixture, is uniform. They are uniformly distributed. So a solution, true solution, is a homogeneous mixture. If you look at the appearance, the true solution is transparent. The solutions may be colored, but they are transparent. However, the suspensions, we know they are opaque, and as you can see, the mud, this is opaque, and the colloidal solution, they are translucent, and they are close to, also they are also close to water. Okay. So now the particle size, if you look at the particle size in true solution, it is much smaller, and as I said, it should be smaller than 1 nanometer. size, and the particle size is much smaller or smaller than 1 nanometer, and so they cannot be particles cannot be seen. But in suspension, the particle size is larger than 1000 nanometer. In suspension, the particle size larger than 1000 nanometer, and so the particle size is very large, and they can be seen even by naked eye or through a magnifying glass. But in colloidal solution, as we see, the particle size is between the two solution and the suspension, so the particle size should be between 1 to 1000 nanometer. So you can just remember the particle size between for the colloidal solution should be 1 to 1000 nanometer. Now above 1000 nanometer you can understand very easily there is a particle size for suspension, and below 1 nanometer particle size for true solution, because the colloidal solution it comes with the particle size it comes between true solution and the suspension. So it defines the boundary. And now the solutions do not settle down when they are left undisturbed. This is what the properties of solution that we have seen. But the suspensions, the solute particles settle down when they left undisturbed. On colloidal solution, the solute particles do not settle down when they left undisturbed. And what is the solute particles and the solvent for the colloidal solution? We use a separate terms. Please note that we do not tell solute or solvent for the colloidal solution, but analogously, these terms we can use here to understand or to just compare the true solution suspension and colloidal solutions. Now the filtration separation is not possible for the true solution, but the filtration separation is possible for the suspension, but the colloidal particles, again the filtration separation is not possible. So what we see, the opacity of this property of colloid is closer to the suspension, and this heterogeneous, they are both a heterogeneous mixture, but what we see, they do not, this, now the particles of colloidal solutions do not settle down. This property of colloid resembles to the properties of true solution, and also what we see, the filtration of the colloidal particles are not possible as we see in the case of true solution, but the filtration of the suspension or the particles are possible for the suspension. And the examples we see, the salt solution is a true solution, a milk is a colloidal solution, and a suspension is a sand in water or some mud. Now, the usually what we know, the colloidal particles are aggregates of hundreds or thousands of molecules. This is what I have said earlier. But some, such as proteins and polymer molecules, I mean some colloidal particles are not aggregates, but they are a single large molecule. And these examples are proteins or polymer molecules, proteins, and then even the nucleic acid. They are into the solution, the aqueous medium in the living cells, and even a single large protein molecule or single large nucleic acid, they have solutions. If you look at one forms, its range, its size is between 1 to 100 nanometer, and it forms a colloidal particle. And so some polymer molecules, artificial polymers are also formed colloid, and these polymer molecules usually they contain only one molecule into that colloidal solvent. That means only one molecule will be in the range of colloidal particle. The proteins and synthetic polymers molecules that form colloids may have molecular masses ranging from a few thousand to many million atomic mass units, and these atomic mass units are also called Daltons that we know. So these synthetic polymers are proteins, which is a natural polymer. These molecules they form the colloids, and which may have the molecular mass that range between thousand to many million atomic mass, means thousand to many million Dalton. So analogous to identifying solutions components as solute and solvent, the colloid components are likewise classified according to their relative amount. So what we know till now, first of all, we understand as we so say in the see in the case of solution, we call solute and solvent. The similar terms for the colloids we call the solutes are called dispersed phase, and the solutions for the colloid even can call as the dispersion medium. So analogous to the definition that we have given for the solute and the solvent for true solution. What is a solvent? The component of the solution which is in excess is called the solvent. Here the dispersion medium is the analogous word to the solvent, and so the dispersion medium is what? The component of the colloid which is larger in amount, which is in excess, is called the dispersion medium, and the one which is in a small amount, the minor amount, is called dispersed phase. The solute, as we know, the solute is what? The component of solution which is in minor amount, which is in the smaller amount, is dispersed. This is the solute, and for the colloids, it is the dispersed phase. The solute, the analogous name for the colloids is dispersed phase. So the particulate component typically present in a relatively minor amount is called the dispersed phase in a colloid, and the substance or a solution throughout which the particulate is dispersed is called dispersion medium. So this is dispersion medium, the substance throughout which the particulate is dispersed, and dispersion is dispersed phase is dispersed is called the dispersion medium. And the colloid may involve virtually any combination of physical state gas, liquid, solid or solid gas. With any combination of then it forms the colloidal particles. The colloid examples we will see, and this we will see examples in more details and what does this sentence mean later on. Let us now see the differences between dispersed phase and dispersion medium. The dispersed phase is what? Dispersed phase is analogous to solute, and dispersion medium is analogous to the solvent. And the dispersed phase is one of the two phases in a colloid, and dispersion medium is also one of the two phases in the colloid. Now what we see, the dispersed phase is discontinuous. So dispersed phase, the particle like solute, as we see in the solution, they will be here, there, not everywhere. But for the solvent, we see they are continuous in the solution. Similarly, here the dispersion medium will be continuous. So dispersion medium is a continuous phase of a colloid, and the dispersed phase is known as internal phase, and the dispersion medium is known as external phase. The example of dispersed phase is dust particle in the air. The dispersed particle, whatever we know, the particles of the dust in the air, particles of dust in the air, it forms a colloid. So air is a colloid, and this dust particles are dispersed phase. Now, if you look at another colloid, the water, that is milk. So water in which the uh, fats are dissolved. So this water butter fats are dispersed. So the butter fat is what this dispersed phase, and the water is what the dispersion medium. So here also the for the dust particles in air this is what the air is dispersion medium, but the dust particles are what dust particles are dispersed phase. Now let us look into classification of colloids. The colloids are classified on the basis of certain criteria, and there are three criteria that we are going to study. One is the physical state of dispersed phase and dispersion medium. So in what physical state dispersed phase and dispersion mediums are there, and this sentence that we have said any physical state that, so this will come into this classification, will come into the classification of colloids based on the dispersed physical state of dispersed phase and dispersion medium. And then comes the nature of interaction between dispersed phase and the dispersion medium. So what is the kind of interaction that is there between dispersed phase and dispersion medium? So based on that, colloids are also divided into different classes. So this is one way of classifying colloids. And another way, the third way, is the type of particles of the dispersed phase. So what kind of type of particles are there? Means the colloidal particles, the dispersed phase is made up of only one molecule, the large molecule, the polymer molecule, or it is aggregates of many small molecules, and so on. So this way, this classification is actually done. Let us first look into the classification of colloid based on physical state of dispersed phase and dispersion medium. So dispersed phase and dispersion medium come on their physical state. So what we know, there are three physical states that is possible for a substance, and these are solid, liquid, and gas. So whether it is dispersed phase or dispersion medium, they can be solid, liquid, or gaseous phases or the gaseous state. However, if you look into the mixture of one gas into another gas, it will always form a homogeneous mixture, and homogeneous mixture is whenever it forms, always forms homogeneous mixture, so it will not form colloid. It means the gas molecules, if the gas molecules are there, they will not naturally aggregate one together to form particle size, particles of the colloidal size, and so the gas until unless there is not something else that makes it to happen or forces it to happen. So gas in gas, if they interact, a gas molecule interacts with a gas molecule, it will never aggregate to form a particle of the colloidal size. So a mixture of gas with another gas do not form a colloidal system, but a homogeneous mixture. Other than that, a gas into a liquid, a gas in a solid, or a liquid in solid liquid gas, or a solid in solid liquid gas. So what can we see? There are eight types of possible colloidal systems based on the physical state. So depending upon whether the dispersed phase and dispersion medium are solids, liquids, or gases, eight types of colloidal systems are possible. And these colloidal systems are based on the physical state of dispersed phase and dispersion medium and all the possibilities that we can consider. So many familiar commercial products and natural objects are colloids. For example, whipped cream. Whipped cream is a foam, and this foam is also a colloid and a gas dispersed in a liquid. A foam is what? A definition is a colloid, and this type of colloid is what? A gas dispersed in a liquid. So gas is what? Gas is dispersed phase for a foam, and the liquid is the dispersion medium. So most biological fluids are salts or aqueous salts. And these salts were, what is the definition of salt? The solid dispersed in the water or the liquid. For example, in the biological cells, what is the dispersion medium is water, and the solid particles, the many cell organelles, they are dispersed into this. So the most biological fluids, and these biological fluids will contain protein actually. Even the serum that we see for the blood, it contains albumin protein. So the proteins, these protein molecules are larger, so they will what? They they form salts, and this is an example. What is the example of biological fluids are examples of colloidal system. The proteins and nucleic acids are colloidal sized particles dispersed in an aqueous solution of ions and small molecules within a typical cell. This I have already explained. Now the firefighting foams used at emergency airplane landing are also colloidal systems. Out of the various types of colloids, the most common are gels, and gel is what? The dispersed phase is liquid and the dispersion medium is solid. So gel is what? A colloidal system of liquids in solid. This is called. And the emulsion is what? Emulsion is liquids in liquid. So dispersed phase is also a liquid and dispersion medium is also a liquid. Example of the milk that I have seen. The butter fat is also a liquid and the water is also liquid, and this is the emulsion. The milk is an emulsion. Now the salts are also very common, and salts like salt is what? Solids in liquids. This definition we have already seen. The aqueous salts means what? The dispersion medium is water, and if it is dispersion medium is any liquid, so that is what solid in a liquid, and this we call a salt. So generally it is salt. So if the dispersion medium is water, the salt is called aqueous salt, and that is what we have seen here, the aqueous salt or aqueous salt. And if the dispersion medium is alcohol, the salt is called alkosol. The aqueous salts or hydrosols, it also represents water, and aqueous salts. So salts, the dispersion medium is water, and if the dispersion medium is alcohol, which is another type of liquid that we know the chemical nature, the organic molecules, organic compound having carbon and OH group, hydroxyl group as a functional group, this is alcohol. And so such salts or the colloidal salts are called alkosols if the dispersion medium is alcohol. So alcohol making salt as a when it is used as a dispersion medium, alkosol. Now we will see all types of eight types of colloidal systems depending on the different dispersed phase and dispersion medium, and what we have seen that gas a gas mixture will never form a colloid. It will form always a homogeneous mixture, but colloids are heterogeneous mixture, so that example will not be there. But a gas being dispersed phase with the dispersion medium having a liquid, we can have such colloids. And so the liquids can make this gas molecules aggregate to get into the size of the to come into the colloidal particle size. So the example is foam. So gas being dispersed phase and liquid being dispersion medium. This colloid, name of this colloid is called foam, and the common examples are soap lather, froth, whipped cream, soda water. Soda water or the cold drinks bottle you might have seen many small, and the beaten eggs, beaten egg whites, foam, And so these are examples, common example of the foam. And foam is what? It's a colloidal system of a gas being a dispersed phase and a liquid being the dispersion medium. And if the dispersed phase is a gas and but the dispersion medium is solid, if so such colloids are called solid foam, and is not much important and not such famous. So one can call it as a solid foam. And the example is cake, bread, pumice stone lava, floating soaps. These are examples of what? Gas into solid colloidal system, and gas into solid colloidal system, which is called solid form. For example, cake, bread, pumice stone lava, floating soaps, etc. Now the liquid into gas, liquid being dispersed phase, it can form colloids with gas being the dispersion medium, or liquid being the dispersion medium, or solid being the dispersion medium. All the possibilities that we are considering. So the dispersed phase can be gas, liquid, or in the gaseous state, or liquid state, or solid state. Dispersion medium can also be in the gaseous state, liquid state, or the gaseous state. The only thing is the gas into gas cannot form a colloid. So there are 3 into 3, 9 possibilities. Out of that 9 possibilities, gas into gas is not a possibility. It do not form colloid. So that is why we have 8 different possibilities, different types of colloidal system, so based on the physical states of dispersed phase and dispersion medium. Now that we see the liquid into gas, the liquid is dispersed phase and gas is dispersion medium, and such colloids are called aerosols. So please remember this is aerosol. The example, this is important. The definition: liquid is the dispersed phase and gas is dispersion medium. So the liquid in gas. So liquid in gas. So what we see such example: mists, fogs, clouds, sprays. These are all liquid, small liquid particles. So they are into the gas, being the dispersion medium, and so they are examples of aerosols. So the mist, fogs, clouds, sprays, they are examples of aerosols. The aerosol is what? It is a kind of colloidal system in which dispersed phase is a liquid and the dispersion medium is a gas. Now, if we see also the solid aerosols, when those things that this will come a bit later. Now the dispersed phase being liquid and dispersion medium being liquid. The example is emulsion, and the definition I have also provided here. Liquid is liquid. So dispersed phase and dispersion medium both are liquid. We see the say the colloidal such colloidal system as emulsion. And the example is mayonnaise. So mayonnaise what? Oil in vinegar, and is what mayonnaise. So oil, dispersed phase, and vinegar dispersion medium, and using them we form mayonnaise, and so mayonnaise is an emulsion. Butter, we know, the milk is also an example of emulsion. Hair cream, oil mixed in water. Oil mixed in water is something like sometimes what happens, the oil spills in oceans, that oil, the petroleum oil that we bring to the ships. And what happens because of the water waves, these oil particles, the large particle, whatever it is, fills out on the, and initially it floats on the surface of the oceans, and because of the water waves, these oil particles, a large mass of oil, splits into very small particles, and these particles come into after some time into the size of colloidal particles, and so it forms a colloid, and once it forms a colloidal into the oceans. Now the oil cannot be separated out from the oil, from the ocean, because it forms a colloidal system, and that is there. It will go and dissolve. It will never settle down into the oceans, and it will here and there, and so it causes what it causes pollution into the oceans. So the oil mixed in water is one example. And for the emulsion, one thing is that we also need some emulsifying agent to make this emulsion stable. Like for the milk, the casein protein is used, is present as the emulsifying agent. And because of the presence of casein proteins, this dispersed phase and dispersion medium, they do not get separated out. The mayonnaise, we use yolk egg as the as the emulsifying agent. So now let's look into the another type of colloidal system, liquids in solids. So liquid is the being dispersed phase and a solid being dispersion medium. And the example, this the such colloidal systems are called gel. And the example you might have seen the cheese. Cheese is example of gel, and it is what the liquid in solid. So dispersed phase is liquid, and the dispersion medium is solid. Other jellies, pearl, opal. Opal is what? Water in silica. So water is what? Dispersed phase, which is a liquid, and the silica SiO2. This what? It's a solid that we know, and a solid silica is dispersion medium, which is a solid. So this is opal is also an example of a gel, means a colloidal system having dispersed phase a liquid and dispersion medium a solid. Now another system of the solid, if the dispersed phase is solid, and so dispersed phase solid, it can also form colloid with all the other phases, uh, dispersion medium in all the three different phases. So now the solid in gas, and a solid in gas, like liquid in gas forms aerosols, so solid in gas forms solid aerosols. And the solid aerosols are examples of smoke, fumes, dust. There is a difference between a smoke and fume. A smoke, anything because of the combustion, the particles that comes out, it forms a smoke. The smokes usually do not have a smell. However, the fumes are a smell. So for fumes, we do not need always a combustion. For fumes, sometimes some rotten substance also it a smell comes out if from the rotten substance, and that is what that because of that smell, so this is called fumes. So that there is a difference between smoke, fumes, and dust. These are what the solid particles are there, and they are dispersed into the gas, they, and so they form solid aerosols. And these are examples of smoke, fumes, and dust are, and the dust particles that are there into the air. They also form solid aerosols, and these solid aerosols. So this is example of the, this type of colloid. Means the solid aerosol means the dispersed phase is solid, and a dispersion medium is a gas. Now the dispersed phase being solid and dispersion medium being a liquid, it forms salts, and this is also very important. So this definition is also important because this first phase is what? Solid for salt, and dispersion medium is liquid. And the examples are paints. Usually these pigments, they are solids and we mix them into the oil, so kerosene oil and so. So these paints are what? They are salts. So salts means solid, dispersed phase is solid, and dispersion medium is a liquid. Cell fluids, or the cell fluids, what dispersed phase, solid, dispersion medium, liquid. So some inks are also salts. Starch in water, the mud that we see, that is also a starch in water. So it's an example of salt. Milk of magnesia means the solution of MgOH twice in water. That is milk of magnesia. That is also an example of salt. Now the solid into solid and solid in a solid is an example of solid split salts, and solid such fluids may be called as solid salts, and the example is some alloys. You know the alloys, Mishra Dhatu in Hindi we call, and some colored glasses. Some colored glasses are also example of solid salts, and solid salts are what? Solid in solid, means the dispersed phase solid, dispersion medium solid. And all other gemstones, they are also example of solid salts. Now let us look into the classification of colloid based on nature of interaction between dispersed phase and dispersion medium. And dispersed phase and dispersion medium, what can be the interaction between them? If the dispersion medium suppose is a liquid and dispersed phase is a solid, then this kind of classification one can make. And so this depending upon the nature of interactions between dispersed phase and dispersion medium, colloids are divided into two different categories, and one category is called a lyophilic colloid. And lyophilic means the solvent attracting or the solvent loving colloid, and the lyophobic colloid. Phobic means the repelling that we know or the hating. The lyophilic means the solvent repelling or solvent hating colloid. So the dispersed phase will not love, or it will not be having very strong interaction with the solvent of the dispersion medium, and so we call such colloids as lyophobic colloids. And if the dispersion medium is water, so these terms are changed. So lyophilic, if the dispersion medium is water, we call it hydrophilic, and hydrophobic. Hydrophilic means water loving, and hydrophobic means water hating. So that the colloidal systems are there. Now let's look into one both the types of colloids, the lyophilic colloids. As we know, the lyophilic word that from the Greek word, the etymology, lyophilic means the liquid loving, and the liquid loving, the lyophilic colloids are thus lyophilic salts. And why they are salts? Because the dispersion medium we are considering here is a liquid. Because we are calling it a solvent attracting or solvent loving or solvent repelling or solvent hating. And whenever we are calling solvent, it means the dispersion medium is a liquid. And so they are salts in dispersion medium are liquid, they are salts, and dispersed phase we are considering as solid. And so the dispersed phase solid and dispersion medium liquid, these are their salts. You can see here in this definition. So they are also called colloidal salts or lyophilic salts. And so the colloidal salts directly formed by mixing substances like gum, gelatin, starch, rubber, etc. with a suitable liquid, the dispersion medium, which is this liquid we call the dispersion medium, are called lyophilic salts. So these substances, gum, gelatin, starch, rubber, they have very strong interaction with the water molecule because they have three OH groups in the rubber. So this they have particularly starch, gelatin, and so they have very strong interaction with the water. So they are water loving colloids. They form a water loving colloids. And so if the dispersion medium is separated from for this colloidal system, so they form lyophilic salts or lyophilic colloids. Since the gum, gelatin, starch, rubber, they have a strong interaction with the water because of the hydrogen bonding. And so if the dispersion medium is separated from the dispersed phase, and how it will be separated, maybe because of the evaporation. So the salts can be reconstituted by simply remixing with the dispersion medium. And once suppose the solvent of the dispersion medium is evaporated. So and this once it is evaporated, so the dispersed phase and dispersion medium are now separated. Once as soon as you put the dispersion medium and the water again into the solution dispersed phase and mix it properly, these salts will again be formed, and thus these salts are called reversible salts. A reversible salt means they can be formed again even once the dispersion medium was evaporated. So this that is why it is a reversible salt. And these salts are very stable and do not get easily coagulated. And these salts, because of the interaction of the dispersion medium, they are very stable salts and they do not easily get coagulated. And let us now look at the lyophilic salts. The lyophilic, the word meaning we do know, and the meaning is liquid heating. The lyophilic phobic means liquid heating, and we know if the dispersion medium is water, it is hydrophobic. So when mixed with the dispersion medium, substances like metals, their sulfides, etc. do not form the colloidal salts. So although the metals and their sulfides are solid, but when they mix with the dispersion medium, usually they will not form because metals and their sulfides are heavy and these particles they not form the colloids very easily and they do not have much interaction with the water. And so what happens that they do not form such a colloidal system very easily. For the making colloidal system, we need a special method. So their colloidal salts are prepared by a special method, and such salts are called lyophobic salts. So why? Because they have not much interaction, a strong interaction with the water, so they do not get easily separated out. So this means the solid is the metals. Metals they do not go. Atoms are not separated out, and when they get aggregated to form colloidal particles. And so we call such salts as lyophobic salts or lyophobic colloids. But we can make such colloidal system using a special method, and such colloidal system for which we require a special method to form is called the lyophobic colloid, and such salts are called lyophobic salts. These salts are readily precipitated or coagulated on addition of small amounts of electrolytes, and this gets easily coagulated or the precipitated with salts means the lyophobic colloids or lyophobic salts on addition of very small amount of electrolyte or heating or by shaking, and hence they are not stable. So the lyophobic colloids are not stable, but lyophilic colloids are stable. And also, once precipitated, these lyophobic colloids do not get back to the colloidal salt by simply addition of the dispersion medium. And because again, once they get precipitated out, we again the same special method for preparing this lyophobic salt. and it will not form again just by adding dispersion medium, as we have seen in the case of lyophilic salts. So the lyophobic salts are also called irreversible salts. And lyophobic salts need a stabilizing agent for their preservation, and these lyophobic salts need a stabilizing agent for their preservation. So if you want them to keep as such for the larger period, so you have to use some agents, a stabilizing agent, for make them stable, to make these lyophobic salts stable. So now let's see the difference between lyophobic and lyophilic and lyophobic salts one by one. So properties just to compare. So these are solvents or the dispersion medium loving. The lyophilic salts are what? They are dispersion medium loving colloids. But the lyophobic colloids are, they are dispersion medium hating colloids. Lyophilic colloids are thermodynamically stable. Lyophobic colloids are thermodynamically not stable. And this, because for their stability, we need some stabilizing agent. And they can, even by just addition of a small amount of electrolyte, or even by heating or shaking, they will be separated out. So dispersion medium and dispersed phase will be separated out. The precipitation in lyophobic soil is a reversible process that we have seen. Once the dispersion medium is evaporated or separated out by any other method, just by adding the dispersion medium, you can again form the lyophilic salts, but such things are not possible with the lyophobic salts. We need a special method for making lyophobic salts. And once the dispersed phase is separated out, we again need the same special method to again form the lyophobic salts. So, and what are those special methods? Some special methods we'll see later on when we will study the method for the preparation of the colloids. So a strong attraction force works between colloids and the liquids in lyophilic salts. The strong attraction force, and these forces are usually the van der Waals interaction. So this some attraction force works between the particles of dispersed phase and dispersion medium in lyophilic colloids, but there is either no or less or the weaker attraction force that works between colloidal particles and the dispersion medium in lyophobic colloids. Either there is no attraction or there is very weak attraction in the lyophobic colloids between dispersed phase and dispersion medium. The lyophilic colloids are, they are highly viscous, and the lyophobic colloids have same viscosity as that of the dispersion medium or the pure solvent of it. The lyophilic colloids, they form lyophilic salts. So this thing is not needed. Now the lyophilic salts are prepared by direct addition of colloids into the liquid, means the dispersed phase into the dispersion medium. But the lyophobic colloids, for making the lyophobic colloids, we need to use a special techniques, because just by adding dispersed phase and dispersion medium, they will not form the colloidal system. So we need a special techniques to form such colloidal systems. This is colloidal, the lyophobic salts, the lyophobic colloids. Now let us see the classification of colloids based on particles of dispersed phase. And the particles of dispersed phase, so depending upon the types of particles of the dispersed phase, colloids are classified as multimolecular, macromolecular, and associated colloids. Please see the association or aggregation we will see in the case of multimolecular and associated colloids both, but they are defined separately. We'll see what are the difference. And so the multimolecular colloids, as the name itself defines, the many molecules will aggregate to form the colloid particles. Then the macromolecular, this is only one molecule, but a very large molecule, which will be the dimension of the colloidal particles, and so it is the multimolecular. And associated colloids, you see what is difference of the associated colloid with the multiple molecular colloid as we proceed further. Now let's see the multimolecular colloids. So when on dilution, atoms or smaller molecules of a substance aggregate together to form particles of colloidal dimension. And these particles, so what will happen, the atoms or molecules, the small molecules, they will aggregate together to form larger particles of colloidal dimension. This larger particle should be the dimension of the colloid, and that is between 1 to 1000 nanometer. And thus the formed colloid are called multimolecular colloids. And thus in these salts, the dispersed phase consists of aggregates of atoms or molecules. So this first phase is what? The colloidal particles. These aggregates of atoms or molecules. And so the particles are held together here by van der Waals forces in these colloids. The weak van der Waals forces will be there between the many atoms or molecules which are joined together to form colloidal particles of the dispersed phase. And these they usually have lyophilic character, and these particles means the dispersed phase usually have lyophilic character. Now the examples are the gold sol. The gold atoms aggregate to form colloid particles of various sizes. The gold atoms here, these are atoms, the aggregated particles are the particles which aggregate are atoms, and the atoms of gold they aggregate to form colloidal particles of various sizes. And the sulfur salts. Sulfur salts contains aggregates of S8 molecules. We know sulfur usually forms the molecules with 8 atoms bonding together, and see the eight molecules when they join together by weak van der Waals interactions, they form colloidal systems. And this we call the sulfur salts. The examples are this. And, and let's now look this macromolecular colloids, the definition. The macro means the very large, a molecule means a molecule. So very large, one very large molecule will be of the size of the colloidal particle. So macromolecules in suitable solvents form solution in which size of macromolecules may be in the colloidal range. And if the size of the macromolecule in the colloidal range, and when it is dissolved in the solvent, it forms macromolecular colloids, and such colloidal systems are called macromolecular colloids. And these macromolecules forming the dispersed phase are generally polymers having very high molecular mass. And the macromolecule means the large molecules are what? They are usually polymers. They may be the synthetic polymer, or they may be the natural polymers. Natural polymers we know the starch, the gelatin, cellulose, proteins, nucleic acids, they are natural polymers. But we see that there are many other polymers, the synthetic polymers, they also are macromolecules, and they also form colloidal systems. So these colloids, the macromolecular colloids, are quite stable and resemble two solutions in many respects. And so these were what this colloidal system, that quite they are very stable. And why they are stable? Because one molecule is dispersed everywhere. And so what we see also in the true solution, although the true solution, the particles, the chemical particles of solution, we initially we consider very smaller in size. They are tiny atoms. Their dimension is less than 1 nanometer, and they form solution. Here, what is happens is also large molecules, and these molecules, because they are one molecule, so they will be together, and the one molecule, and then the dispersion medium we see, which is a solvent, and this one molecule separated out with the dispersion medium many places. So it resembles quite of the true solution. And so these colloids are quite stable and resembles to solution in many respects. And they have usually lyophobic character. So as we know, the protein solution proteins usually have the hydrophobic character. And this protein folding happens because of the hydrophobic colloids, and these are the most accepted theory. And that usually doesn't mean it will always happen. So the naturally occurring macromolecules that form macromolecular colloids are starch, cellulose, proteins, enzymes, gelatin, and as we know the starch it forms lyophilic colloid starch. So it usually means it is not means it will not always happen. And so the artificial macromolecules are synthetic polymers such as nylon, polythene, plastics, polystyrene, etc. They also form macromolecular colloids. Now let us look into the associated colloids, and which are also called micelles. And the associated colloids we have seen earlier, and earlier we have seen multimolecular colloids. They are also aggregate. Associated colloids, they are not, they get associated, and this association, because also the multimolecular colloids, they are usually have lyophilic character, but these associative colloids, they have in the one molecule in the dispersed phase, these molecules have both lyophilic and lyophobic character. The certain substances on dilution in a medium behave as normal electrolyte. So on dilution in a very diluted medium, they behave as a normal electrolyte. But as you increase the concentration, they started getting associated, and they form, because of the association, they form aggregates, and these aggregates will be of the size of the colloidal range, and so they form colloids. Usually, what we see for the multimolecular colloids, the dilution, if you know the definition, is not based on the dilution, but these associated colloids on the very diluted condition, they behave as a normal electrolyte, and on increasing the concentration, or if they are in higher concentration or above certain concentration, they form the aggregates, and these aggregates are the colloidal particles, and the colloids thus formed are called associated colloids, and the aggregated particles which are of the colloidal range are called micelles. And the micelles, we know micelles are formed because of the soap or and detergents, and the examples that we know. So these are associated colloids. So these aggregated particles are called micelles. So the certain substances on dilution in a medium behave as a normal electrolytes at low concentration, but behave as a colloidal particles at higher concentration due to the formation of aggregates. The colloids thus formed are called associated colloids, and the aggregated particles are called micelles. The formation of the formation of micelle takes place only above a particular temperature, which is called crash temperature. So the micelle formation require a temperature with minimum temperature, which we call the crash temperature. So above this crash temperature, the micelle formation will happen. So below this temperature, this micelle formation will not happen. So the colloidal, the associated colloid will not form below this a particular temperature, and this temperature is called crash temperature. And above a particular concentration, only the micelle formation happens, and this concentration is called, as we know that a lower concentration micelle formation won't happen, and these particles which are forming micelle at higher concentration behave as electrolytes or pure electrolytes at lower concentration, and this the concentration, that concentration, the threshold concentration is called critical micelle concentration. The threshold temperature for the formation of micelle is called crash temperature, and this threshold concentration is called critical micelle concentration, or CMC in short. So the formation of micelle takes place only above a particular temperature, which is called crash temperature, and above particular concentration called critical micelle concentration, or CMC in short. Micelles may contain as many as 100 molecules or even more. So each micelle, which is actually associated colloid, it may contain 100 molecules or even more than that. These colloids have both lyophobic and lyophilic parts, and we will see their structure later on when we will see the mechanism of micelle formation. And so the soaps and detergents, they have both hydrophobic and hydrophilic parts, and that we call antipathic molecules. Usually they are the fatty acid chains, and the salt formation, that we'll see their chemical structure in the next class. So these colloids have both lyophobic and lyophilic parts, so associated colloids. The dispersed phase have both lyophobic and lyophilic parts. And so these colloids revert to individual particles on dilution, which are usually ions. So what happens on further dilution, once the micelle is formed and once you do further dilution and shake the solution, what we'll see that these individual ions will be separated out. The minimum concentration required for micelle formation depends upon the nature of the dispersed phase. So what is the nature or the chemical nature of the dispersed phase? Depending on that, the critical micelle concentration also depends. So CMC required for the micelle formation depends on the dispersed phase, so it's property of the dispersed phase. The dispersed phase means that here the solute particles like detergent and soaps, their property, and what kind of detergent, what kind of soaps, what is the length of the fatty this hydrocarbon chain into that fatty acid or that detergent or the soap. The associated colloids are usually formed by surfactants, and here we need surfactants, the surface active agents. Surfactants are surface active agents like soaps and synthetic detergents, and the soaps or synthetic detergents are called surfactants, and that is why they form associated colloids or the micelles. And these agents form micelle when present in solution at a concentration greater than CMC, and they form micelle only when the concentration is greater than CMC a certain value, and for soaps, the CMC is 10 to the power minus 4 to 10 to the power minus 3 mole per liter, and the CMC critical mild cell concentration for soaps is it ranges between 10 to the power minus 4 to 10 to the power minus 3 mole per liter in molar. I'll stop it here. On the next class, we'll see the mechanism of micelle formation in soap solution and other things. In the next class, I'll okay.